So as for our learning objectives for this topic, so we'll have these three as our guide that we will be able to check at the end. You learners can check at the end if you were able to accomplish or achieve this particular learning objectives. So you should be able to calculate work done by a varying force or force that is not constant, calculate work done by springs, and calculate work done in pumping of fluids. So these are the three different types of work that you will be taught how to quantify using the definite integral. Now, in your physics, you have learned that when a constant force is being applied in the direction of the motion of the object or in the same direction as the displacement of the object, the displacement being d, now the product of such force and displacement is work. So this is how we define it, basically fundamentally in physics. So the force here that is being applied is constant. The direction of the force and the direction of the displacement has to be the same for work to be applied. If the object is displaced in a different direction than the direction of the force that is being applied on it, no work is done by the force that is being mentioned, because it is a requirement that the direction of the force and the displacement has to be the same for work to be done by that particular force. Now, this is your physics. Now, examples of this are the two that are indicated here. So let's say an object moves 5 feet along a line while subjected to a constant force of 100 pounds in the direction of motion. So take note, there is the specification that the movement of the object is in the direction of motion. So the movement or the displacement is 5 feet, and this is the amount of force applied. And it is, take note, constant. So based on the definition of work, so being force times the displacement, so you have 100 pounds times 5 feet. So the work that is being applied by this 100-pound force is 500 foot-pounds, or pound force per foot, foot-pound force. Okay, not per foot, but foot-pound force. Now this is an English problem or a problem using English set of units. Now what about, let's say we try another problem which uses SI, sets of units. So an object moves, so this is the displacement 25 meters along a line while subjected to a constant force of 4 newtons in the direction of motion again. So it's always specified that the force is the same as the direction of motion. That way your work will not be equal to 0. So what is done is we multiply the force of 4 newtons to 25 meters, which is the displacement. So the answer is 100 Newton meter. This Newton meter unit is the joule unit. Okay, so this is the usual work, the kind of work problems that we have encountered in physics regarding the application of the formula work is equal to the force times the displacement, or the distance traveled in the direction of the force. So this is just but a short review. Now in our case, what about work done by a variable force applied in the direction of motion? Or suppose that an object moves in the positive direction along a coordinate line while subjected to a variable force. And take note, this variable force is f of x. Okay, f of x. Now it is applied in the direction of motion. Now define what is meant by work performed by this particular variable force on the direction as the object, as the object moves from. So this is the displacement of the object from x equal to a to x equal to b. And find a formula for computing the work. So this kind of work, how will you or what will be your corresponding formula, since in this case your force is varying and it's in the same direction as the displacement, and the displacement is from A to B. Okay, so what will be your formula? But before we know this particular formula, you have here on the left side an illustration of how can a variable force be the cause of work being done on the object. So the example that is being done here is this block attached to a spring, which is attached to this part of a certain wall. This A here, the A here is the natural position of the spring, meaning this is the rested position of the spring, and as such the block is not moving as well. So they are both at rest, referring to the block and referring to the spring, assuming that there's no friction on the floor in which this particular block rests. Now, if we're going to apply force on this block, correspondingly, the spring is going to stretch, and there's going to be spring work, or the work done on the spring to have it stretch. But our concern right now is not the spring work, but just a simple case or an illustration when work is a case in which the force is varying. If you have noticed, class, if you initially stretch the spring, the force that you're applying on it will be different if it's already in its most stretched position. What I mean is, over time, as we continue to stretch the spring, as we continue to elongate the spring and we apply force on this block in which the spring is attached to, there's a need for us to increase the force we are applying on this block. That way, our spring gets to elongate more. So this is a case wherein the force is not fixed because the force is dependent on the manner in which the spring stretches already. The more elongation we expect on the spring, the more force is to be applied on this block. That way, the spring will remain stretched, or it will even be stretched the more. So this is a case wherein the force is not constant. So if you want to pull the block attached to the spring horizontally, then you should have to apply more and more force to the block to overcome the increasing force of the stretching spring, considering that there is no friction on the floor that is also, shall I say, hindering from the block to move to the right. Okay, so this is variable force. Now going back to the question, then what should be our formula in this case wherein force is not constant? Okay, so let me clear first and let me continue. So this is now your work in the case in which the force that is being applied is not constant, or it's a variable force. Now, you have here the limits of your integration as to the displacement of your object. So it is said to be, based on this integration equation, that your object is displaced from A to B, or from position A to B, and its force, or the force that is being applied to it, is a function of its displacement. So you can see that you have here the force as a function of x, where x represents the displacement of the said object. And as such, it's still a requirement, and the requirement that is used then in work equal to force times distance when force is constant, that the force and the displacement, or the direction, is the same, should be applicable as well to this one. So displacement and the direction of the force has to be in the same direction. So as to the succeeding problems that we're going to discuss regarding the application of the definite integral to work-related problems wherein force is variable, this would be it. This is the integral expression. So we'll look into specific applications of this particular integral expression. Okay? Now, let us continue. Unless you have any questions Have any questions? Sige. So now there are no more questions. We proceed. So this is our first example. A 60-meter climbing rope is hanging over the edge of a tall cliff. How much work is performed in pulling the rope up to the top, where the rope has a mass of 66 grams per meter? Second question, how much work is performed pulling a 60-meter climbing rope up a cliff where the rope has a mass of 66 per meter? Seems like the two questions are the same, but they're not. Okay, they're not the same. So I'd like you to read silently the problem while I try to draw the scenario here. That way you can tell me your understanding of the difference between the two questions. Okay, let me just draw first the two scenarios for the two questions. For now, what you can do is you read the problem. Okay, so this is the illustration based on the question that is written here that follows after this statement. Now, based on what you see here on the left, you could see already part of the solution here on the left, the entire solution. What do you think is the difference between the two questions, or what is the first requirement here based on the first question? What's the scenario for this first requirement? And as to the second requirement, what is the scenario? I have it already placed in here. Okay, you can either write on the chat box, I can read your answer for you, or you can raise your hand and then tell the class of what's your understanding of the two scenarios that are written here. What do you think is the difference between the two questions? CHE, anyone? What's the difference between this question A and this question B? I already placed here the illustration. So what do you think should be the interpretation here? Okay. Situation A is pulling the rope in an upward direction, while situation B is pulling towards the cliff face. Situation A is pulling the rope in an upward direction, while situation B is pulling the rope towards the cliff face. Okay? What about the others? I missed something. I'll draw something here. So you can tell me what's your interpretation. Okay, some more? In situation A, the rope gets lighter over time. In situation B, the weight is constant. Very good, Eugenie. Why do you think is in situation A, the weight of the rope gets lighter over time? How is it being pulled up? While in B, why do you say that the weight of the rope is constant in the entire process of pulling the rope up the top of the cliff? Eugenie, very good. That's the correct answer. Why do you think here in B it's a constant, here in A the rope gets lighter? Who can explain what Eugenie already offered as an answer, or the difference between the two? Almost there. Come on, ChE, think. Eugenie already gave you the answer. All you have to do is answer the question why in this scenario A, the rope gets lighter, and in B, its weight is constant. I've drawn it for you already. So what's the difference between what is being asked in A and B? It's actually asking for the same thing, the work. But in the process of determining the work, or in the process of pulling the rope up the face of the cliff, there's the difference. So what is that difference? What about Drus Aujero? Why is it that when you pull rope here in scenario A, it gets lighter, while in B, it's not? Are you there?
I miss,
Okay.
sorry, I got this. I think yes, kay ang direksyon sang rope kapatindog mes ang iyang weight kaga tawag ga spread sa mes sa iyang direction mes so nga easy mo lang siya ma-pull kung ara kasababaw ko.
What about this?
Ang sabiya mes para sa kon bugat siya kay isagi siya ka lugar mes nga gintipon ng kabilugan nga weight sang rope mes.
Okay, thank you for that, Rose. Who can explain? Was another explanation? Or Eugenie, you can explain why you say this one, the weight here gets lighter, where this one here, it's constant. Hmm? Come on, CHE. Think. What about John Mark Labto? Why is in scenario A, the weight or the force becomes smaller over time? In B, it's fixed. What's the difference? Actually, the difference I already drawn here. You could see the difference already. Okay? Because in situation A part of the rope is not subject to gravity anymore after pulling. Okay. Very good, Eugenie. So this is it, ha? Look at the question. When you are asked a question, especially in worded problems, you have to be very observant. Okay, you have to be very observant in the manner it's being asked. Take note of the first question. How much work is performed in pulling the rope up to the top where the rope has a mass of 66 grams per meter? Letter B. How much work is performed in pulling a 60-meter climbing rope up a cliff face where the rope has a mass of 66 grams per meter? In the first question, there was no description of the length of the rope. It was just saying how much is performed or how much work is performed in pulling the rope up to the top where the rope has a mass of 66 grams per meter. So meaning your rope in the first scenario is stretched. It's stretched. In our language, wala siya nakaroll, nagahang siya. So just like what Eugenie is saying, if you pull up the rope, up the cliff, there will be the length that remains suspended at any particular time becomes less and less. Why? Because sa aton language, ginaamat-amat mo siya gani butong pasaka. So, ang weight nga nagabilin, amo na lang na ang kakinahanglan sang force na i-overcome ang weight ng gravity. It becomes lighter because the stretched part of the rope that remains hanging becomes less and less because you're pulling it slowly up to the face of the cliff. So that's the difference of this one from this. In letter B class, I have already rolled it. I have already placed here a rolled 60-meter climbing rope. It's not stretched, meaning this entire thing that is rolled and stretched, you pull it up all at once from this particular elevation up to the face of the cliff. So what happens is this entire weight of this rolled rope, 60-meter rope, is the same all throughout as it goes up. It's fixed. The amount of force that you're going to sustain to have this force reach the top of the or the face of the cliff is the same because it's not stretched. Do you get it? First scenario, your rope is stretched and you're pulling it slowly up the cliff. So the unstretched, the remaining hanging part is decreased over time. Whereas in the case of the second scenario, your rope is rolled. So the weight is fixed. The weight, which is the same force that you're going to apply to it so that you'll be able to transfer it from this elevation up to this face of the cliff. So in the solution, you could see that, let's say, we'll represent X as the amount of rope pulled in. Ano bala ang term na pulled in? Ang ginpasaka nga rope. Sa aton language, ang napasaka mo na nga rope. So if it's X, the amount that has been pulled in, ang nabilin di, that would be 60 minus X. That 60 minus X should be multiplied to the mass of that particular rope per meter length. So this is the length remaining and this is the mass per unit length. Now, if you're wondering why this is 0.066, it's because your mass here class is in grams. If you want your units to all agree, that way you will have joules equivalent to Newton meter, your mass unit should be in kilograms. That was taught to you in physics. So that is why this 66 was converted to kilograms by dividing it by 1,000. So you could see that you already have here 0.066 kilogram per meter. If it's multiplied to the meter unit here for the remaining part of the stretch rope, then that would then be kilogram. The remaining unit here is kilogram. This entire expression here is mass. In physics, you learned that in order for mass to be converted to weight, you need to multiply it with the gravitational constant g. In that case, that's 9.8 meters per second squared. So the mass in kilograms multiplied to 9.8 meters per second squared will have a resulting Newton unit for the force. If we do the maths here, this is the corresponding expression for the force only. But a while ago, we defined work as equal to the force times the displacement. In this case, the displacement is dx. What is that displacement? The displacement of this particular rope, either stretched or unstretched, is 60 meters from the bottom part of the cliff. Because the cliff, it says here, is, did the problem say how tall your cliff is? A 60-meter climbing rope is hanging over the side of a tall cliff. The displacement of this rope is not even mentioned here. That the height of the cliff is not even mentioned here. But you have to be very observant that it is said to be a climbing rope. It's used for climbing. So if this cliff is to be climbed, the rope that you are using on it would be of the same height as the cliff. So even though the problem did not specify how tall your cliff is, it should be as tall as the rope that you're using to climb it. So that is why the limits of your integration here is 0 to 60. Now, if you're allowed me to explain in our language, alangan man nga magamit ka sang rope nga 60 nga ang imo nga cliff ang height niya 80, hindi ka kalabot sa babaw. So based on the first statement here, you are to think that the displacement of this rope from here to here is the same as its length itself, which is also the same as the height of the cliff. So they have to be the same in order for this rope to serve its purpose, and that is for climbing this particular cliff. Now, in the first scenario, so if you're going to have this as the force, and this is the displacement, the dx, then the appropriate unit is 0 to 60. In the unpulled condition of this stretch rope, its displacement is 0 in here. But once you start pulling it up, this particular end of your rope has already been displaced by the corresponding length here of the rope that already reached the face of the cliff. It's the same with this also. At this part here of this rolled rope, it's still 0 displacement. But until it reach the top of the cliff, it's already displaced from its original position by, of course, 60 meters or so. Okay? Though it's not again mentioned that the height of your cliff is 60, it just have to be 60 so that your rope will have to serve its purpose. So for letter A, this is your answer for letter A. The work applied in pulling up this rope on the face of the cliff, 60-meter rope, with mass 66 grams per meter is 1,164.24 joules. Now, what about here in this scenario? So by comparison, consider the work done in lifting the entire rope, which is 60 meters long. So it's rolled, and you are to lift it on the top of the cliff, or you have to transfer it from the bottom part of the cliff to the top portion of the cliff. So the rope weighs 60, its length, that's 60, times the mass per unit length, which is 0.066 kilograms per meter. times the G. So this is the weight that is constant. I like to write C. This is the force. This is the weight that is constant because your rope is rolled. The entire 60-meter rope is pulled up. Perform pulling a 60-meter climbing rope up a cliff face. So the work applied for this force is the amount that you have here, which is 38.808. This is Newton, or the constant weight, will be multiplied to the height of the cliff, which is 60. So this is your displacement. This is the work done in scenario B. This is the work done in the simple definition of work equal to force, the weight, times the distance or the displacement of the weight, which is 60 meters. This is where your ordinary physics is applied. This is where your calculus is applied. So true to what Eugenie said a while ago, pulling up this rope up the top or the face of the cliff will exert lesser force than pulling up the entire rope with a constant weight up the top of the cliff. So you have here 2,328.48 joules of work needed for this rope to be transferred here, this location. Well, this one only needs 1,164.24. Okay, it's, I think, a given. Why? Because as you pull up the rope, the remaining weight there becomes lighter and lighter because a little of the length of the rope is exposed to the force of gravity. Any questions? Have any questions? Okay, so I will clear my markings here and we'll proceed if there aren't any questions. So we'll proceed. Oh, there's a question. Noted, Janessa. Thank you. Okay, so we'll proceed. Now we go to example 2. This is the same as example problem number 1. We're talking of a rope that is being pulled up the top of the cliff. But this time the question or the unknown is different. Okay? Now consider again pulling a 60-meter rope up a cliff face where the rope has a mass of 66 grams per meter. At what point is exactly half the work performed? At what point or at what particular distance is exactly half the work performed? So if I will translate this in Ilonggo para maintindihan sa tanan, ano na kalayo ang pag-pull up mo sang rope or ano na kalayo ang rope halin sa base ng cliff nga nag-spend ka na half sang work nga gin-spend mo sa original na scenario. Okay, so in example 1, we have determined already that this is the work light. Okay? Now, we want to know ano na kataas ang distance nga na-cover or gin-travel sang sini nga rope nga gina-pull up mo kung half pa lang sini ang na-spend. So, this is it. So, for example, from the example 1, we know that the total work is 1,164.24 joules. We want to find the height h such that the work in pulling the rope from a height of x equal to 0 to a height of this certain h is 582.12, half of the 1,164.24. Thus, we want to solve the equation. This is our integral equation now. 582.12 joule is equated to the same expression that you have here. What's the same? The force times the displacement. It is now the limits of integration that was changed. Because you know how far has the rope been pulled up from the base, which is 0x, to a certain height h. where you have already spent half of the total work done here. So then we will do our maths. You know how to process this one. If you have this expanded and you use power rule, this will be the answer. You'll have 38.808x minus 0.3234x squared. So this becomes squared and it has to be divided by 2. So this one has to be divided by 2, giving you a 0.3234. Now limits are 0 to h. So these x variables here will be changed to h and equated to 582. As a result, actually, class, you have a quadratic equation. And all quadratic equations have two answers. So there's a need for you to validate or verify which of your answers in this case will be sensible or acceptable. Not that you simply determine the age here and that you will answer all the age that you have determined. So if you use quadratic equation, your calculators can do that as well for you. You will have two age values. One is 17.57. The other one is 102.43. Now, if your rope is only 60 meters long, then the sensible answer, acceptable or plausible answer is only 17.57. You cannot have a height traveled by a rope which is 60 meters long only, and this is the height traveled 102.43 meters already. We know in our first example that whatever is the length of our rope, that would be also the height of the cliff. So hindi pwede that this is the height of the cliff or the displacement of your rope from the base of the cliff already, because your rope is just 60 meters long. Okay, thus about half the work is done pulling the first 17.57 meters. The other half of the work is done in pulling up the remaining 42.43 meters. Again, going back to what was explained in example 1 by Eugenie. As you pull the rope up the cliff, the weight that is remaining suspended becomes lesser and lesser. So that is why the greatest amount of work that is done is in pulling up this small portion, the 17.57 meters. The rest of the remaining work, the 582.12 is used in pulling up the 42.43. Because you have lesser weight already to pull up. So you have lesser weight, so you have more distance covered for the same amount of work, which is 582.12. Do you get the explanation? Any questions? Any questions, class? Okay, so no questions. We will continue. Example 3. In these 3 examples, class, we have 3 different scenarios. So in examples 1 and 2, it's just like one problem with 3 different questions. In here, one problem with 3 questions as well. Okay? Now, this is a little bit challenging in terms of understanding than the first 2, but we will manage. Okay? Now, a box of 100 pounds of sand is being pulled up at a uniform rate at a distance of 50 feet over 1 minute. The box that contains the sand, stated here, which is 100 pounds, is to be pulled up. So just like the rope, it's to be pulled up at a distance of 50 feet given the time only of 1 minute. The sand is leaking from the box at a rate of 1 pound per second. It tells us that the box must have some hole on it. Why? Because the sand as the box is being pulled up is leaking at this rate. So the box itself you have to consider, has its own weight, which is 5 pounds, and is pulled by a rope weighing 0.2 pounds per foot. So this is now an extension of sample 1. Why I say an extension? You have the rope to consider, which weighs 0.2 pounds per foot. You have the box, which has a fixed weight of 5 pounds. And you have the sun leaking at 1 pound per second from your box. So it escapes the box at 1 pound per second. So per second, and the box is to be pulled at over this distance for a period of 1 minute. So there were 3 questions here to be answered. How much work is done lifting just the rope? So the problem itself guides you into answering the other questions. So it first asks you here in letter A, how much work it is done in just lifting the rope. So then, the same principle you will apply to the rope problem that we have in number 1. Letter B, how much work is done in lifting just the box and the sun? So, na-lift mo na ang rope, subong how much work naman niya ang gamiton sa pag-lift sang box nga may unod nga sand. Pag ang ina nga sand is leaking from the box at a rate of 1 pound per second. And C, what is the total amount of work performed? So, since we're now to consider the total amount of work, it's a given already that whatever is your answer in A and B, you just sum it up and that would be your answer for C. Because the total work done in here is the work done in lifting the rope, pulling up the rope, and the work done in lifting the box which has sand inside it. Okay? So, isa-isa konta lang. So, whenever you have problems like this, that a lot of information are given, you just have to write the information one by one and then process it also piece by piece. Just like the saying, you chew the cow. No matter how big the problem is, if you divide the problem into parts, you chew it piece by piece, it becomes manageable. But if you just simply focus on the entire problem itself, that would be very difficult. You cannot swallow an entire cow. So I'm just using analogy here. So you have to chew it piece by piece. Any problem can be solved while looking at it, or let's say dividing it into fragments, which are easily managed than just compared to having to consider the entire problem as is, where is. Okay, so letter A. We start by forming the force function f of x, but you see there's a subscript r here, meaning it's the force needed to pull up the rope, r for the rope. Now, as in the previous example, referring to example 1, let x denote the amount of rope that is pulled in feet. So, ang amount to nga napasaka na. The weight of the rope with x feet pulled in is, this is the weight already. So, you have the rope, this is the mass of the rope per foot, and this is this mass here. Okay, this is the mass. Now, let's assume that this mass is already, that this is actually force already, not pound mass, but rather we'll assume this is pound force already. So this is the mass or the weight, and this is the amount of rope that is still hanging, because x is the amount that is pulled in. And if the rope is to be pulled in a distance of 50 feet, then the remaining part is 50 minus x, because it was already pulled in x feet. So this is the length remaining. This is not the displacement, I'm sorry, this is the length of the rope that is remaining. Okay? The length of the rope that is remaining. So this is now the weight, which is the force due to the rope only. If you distribute the 0.2 here to the 50 minus x, so you will have 10 minus 0.2x. So the work performed in lifting the rope, the work W sub r is equal to the force that you have here. This is your F sub r, and this is the displacement. What is the displacement? 0 to 50. Okay? The distance is 50 feet. So 0 to 50. So this is the work in pulling up the rope, the entire length of the rope for a distance of 50. Now again, this is on the assumption that the length of your rope and the distance covered or pulled, in which this rope is pulled up with the box, is the same. The length of the rope and the distance in which the box with the rope is to be pulled up is also 50. Okay. Before I go to letter B, do you have any questions in this part in letter A? So, weight per unit foot or length multiplied to the length that is remaining. So, this is the weight of the rope that is hanging, okay, attached to the box. The weight, the force multiplied to the displacement integrated from 0 to 50 is the work done in pulling just the rope. Okay. We'll assume that you follow because there aren't any questions. So we'll go to letter B. Now, so letter B says here, the sand is leaving the box since it's leaking at a rate of 1 pound per second. As the vertical trip is to take 1 minute, what is this 1 minute? This is equivalent to 60 seconds. We know that 60 pounds will have left when the box reaches its final height of 50 feet. How was this arrived at? Or how was this value taken? So 60 seconds times 1 pound per second will give you 60 pounds. So this is the total amount of sand that has already left the box, or that has leaked from the box in the duration of the distance covered. So this is the distance covered for 1 minute. Now again, letting x represent the height of the box, so meaning at any particular level is the box from the base, from where it is from situated, and pulled as it is being pulled up, we have 2 points on the line that describes the weight of the box. So when x is 0, let's say for example, I'll just have again this illustration, and we have here, so you will understand. Let's say this is your box, and there you have this rope here. And just make this. Now, at this particular level here, x equal to 0, the mass or the weight is 100. Now, in it reach a certain portion here, this is 50 feet. That's how we represent feet. Is 50 feet. Here, your x is 50, and mass is. When it reached the top of the cliff, use knock. So This is the top of the cliff. And when it reached this height, the mass remaining is just, so nag-leak na ang 60, so the mass remaining is just 40. This is found, so this is found. So if you want a relationship regarding the force due to the sand, I like to have here due to the sand, not to the rope, because we use R for the rope. That would be in terms of X. That should be in terms of X. So any equation of a line will need a slope, X, plus the y-intercept. I'd like to use a different color here so you will understand. So I'll erase this. Let's say green. This is M and B. This F of S, the force that is needed in lifting the sand would be your Y. So that you will see that your equation here is equal to trying to make this as easily understood as possible. I'll change the font. This is F, and this is Y, this is X, and I'll switch to green again so you'll know. This is M, and this is your force to lift the sand in the box. You get this? I need an equation relating the force to the displacement of the sand which is inside the box. Now I have this sets of values. When X is 50, meaning the box already reached a certain height in which it is to be pulled up, the remaining amount of sand on it is just 40 pounds. When the box is yet not moved, still in rested position, the weight of the sand is 100 pounds because it did not yet start to lift. Now, in this case, your X is X and your Y is M. You get the slope of the line based on what you have learned in analytic geometry. Slope is equal to Y2 minus Y1 over X2 minus X1. Now, your Y2 is, you'll have either which of the two that you're going to use. So, your Y2 is, let's say, 100 or 40. Kagusto ka lang. So, 40, let's say, this is the end. Beginning is 100. Okay? As for X, the X here is 50 minus 0. Okay? The manner it's presented here, it's the other way around. 100 minus 40, 0 minus 50. Either which you do it, you'll still arrive at the slope which is negative 1.2. You get it? So we are taking the slope for this line equation relating the force needed to lift the sand inside the box to the displacement of the box. So that particular slope is already 1.2. So here I'll write y is equal to 1.2x. Now question is, what is this b? This b, based on what you have learned again in analytic geometry, it's the y-intercept. You ask, when is your y equal to 0? When is your y equal to 0? Or where on the, shall I say, the y-axis did your line intersect? That is why it's called the y-intercept. So in this case, this is your y, right? The x is your y. So when is it 0? We have here 100. So it has to be plus 100. You get it? When is your y equal to 0? In this case, your y is x. That is when x is equal to 100. Your m is equal to 100. Now, Miss Nabundayan, kung na mag-inchinte, what's the other way of doing it? So, fine. If you cannot understand that for this y, which is your x equal to 0, this is your b, your y-intercept, which is 100, in these two sets of coordinates that you have, you just substitute. So, if you substitute y equal to 50 in this equation, and substitute x, which is 40 in here, you solve for the b. What do I mean? For example, y is equal to 1.2x plus b. I want to know the b. So I can choose from any of the set of points that I have. X is the y. So I have here 50 equal to 1.2. What is my x here? 40 plus b. So 50, and you have here, by the way, this is negative 1.2. So 40 times 1.2 is b, right? Negative plus b. So b is equal to 100. Is that it? Can you check? I don't have my calculator here with me, so you check. So you have 40 times 1.2. That would be, I will just erase. So you'll have 48. If you've reached 50 for the y, your m is 40. This is just 48. See, if you choose class, the y equal to mx plus b procedure, you'll be getting a b here, which is only 98. So better have this one here. When your y is equal to 0, that is when your x is equal to 0, your y-intercept is equal to 100. So that's why you have here 100. Okay, don't use the sets of coordinates here, because if you use this coordinate, by the way, you will just getting 98, not 100. So you substitute a value of y here, which is equal to 0, and then x here equal, and the y-intercept here is equal to 100 for the b in here. So I will erase this one so that you won't get confused. For x equal to 0, which is comparable to your y-intercept is 100. So that is why we placed here 100 for the b. And that's the thing that we placed in here. Now, you may question, Miss Ali, why I have here 5? Why you have 5, 105? It's because this one is just the weight of the sand alone. It does not contain the weight, or does not consider, doesn't consider the weight of the box. You have to consider the weight of the box, which is, as mentioned in the problem, is 5 pounds. So you have to add 5 here. That is why your total force in this case is negative 1.2x plus 105. You added the constant weight of the box. The box weight is constant at 5 pounds. So it was added in here. Now, this is the force due to the sand now and the box. The sand plus the box. Not just the sand, because the sand is just this. The negative 1.2x plus 100. Now, the sand and the box is negative 1.2x plus 105. This is the displacement. It has to be integrated on the limits 0 to 50, because this is the distance in which your box will be pulled up. So your answer in this case, if you process this is power rule. So you will have negative 1.2x squared divided by 2, and this one would be 105x. And then you substitute the limit 0 to 50. After that, you just get the value, which is 3,750 foot-pound force. This is on the assumption that the mass is already force units, so pound force. The total work will then be the work in lifting the rope, the work in lifting the box with the sand. This would be it. Now, if you use calculus through and through without having to answer first the work in pulling up the rope, the work in pulling up the box in the sand, this would be the two forces that you need to add. The first force is the force due to the weight of the rope. The second is the force due to the box and the sand that it contains. All displaced at distance dx. So it would be integrated from 0 to 50. If you do that, you would still be getting the same answer, which is 4,000 foot-pound force. Okay? Now, do you have any questions? So the key in here, class, is in setting up the equation that relates the force that is needed in lifting the sand inside the box first. So you set up using these two sets of, if likened to a point in the Cartesian plane, two sets of values or two sets of coordinates. One is 0, 100. The other one is 50, 40. Now, this is 40 because from the 100, we subtracted the 60 pounds that has leaked from the box when your box traveled the distance in 1 minute. The distance of 50 feet in 1 minute. And then we added, so this is just for the sand. And then we added the constant weight of the box of 5 pounds here in the 100. So all in all, you have an equation which is this. For the force that is needed in lifting the box with the leaking sand. Any question? Any questions? No questions? Sige, so if there aren't any questions, I'll clear this one. We'll have another 10-minute break before I proceed with the next year. Hooke's law and spring work, wherein we apply integral calculus on. Let's have a 5-minute break, then, 10-minute na lang. 10-minute break, then we come back after 10. So according to Hooke's law, the force required to compress a spring x units from its natural length is proportional to x. And that is, that particular force is equal to kx. So the force is equal to the Hooke's law constant times the, shall I say, the disturbed length of the spring, whether it's the compressed length or it's the stretched length, as long as x is to be viewed as the change in the length of the spring. So whether that spring was stretched, meaning the force was used to lengthen it, or whether that spring is compressed, or if that particular force is used to press the spring. This x is to be viewed as the change in the length of the spring. Okay? A stretched spring x units from its natural length, meaning this is the change in the length of the spring. Now, for example, if a force of 1 Newton stretches a given spring 2 centimeters, then we can say that a force of 5 newtons will stretch that given spring 10 centimeters. How is that? Now, 1 Newton is needed for 2 centimeters. If it's 5 newtons, then this 2 centimeters will be multiplied by 5. So you have 10 centimeters. Now, if you're going to convert the disturbed length of the spring, the units from centimeters to meters, then we'll have something like this. 1 Newton, the force is 1 Newton, the X is equal to 0.02 meters. Now, how did Miss Ali get this? The 2 centimeters that you have here will be divided by 100. That gives you 0.02 meters. 2 centimeters divided by 100 will give you 0.02, and the unit is already converted to meters. So given this particular set of values, class, using this particular formula, you just substitute. So you have 1 Newton is equal to K, the Hooke's law constant, times the disturbed length of the spring in meters. And you'll be able to get the Hooke's law constant, the K that is, as 1 divided by 0.02. This one is in meters already. And that will give you 50 Newton per meter. Okay, so the 50 Newton meter that you're getting here for the Hooke's law constant, or the K in this formula, is just taken from the substitution of 1 Newton for the force and 0.02 meters for the, shall I say, the change in the length of the spring. So this is now your Hooke's law constant. Okay? Now, its value is taken based on the conditions that are stated in the problem. And the condition is this. You apply a force of 1 Newton, it will stretch the spring 2 centimeters. It will change the length of the spring by 2 centimeters. In the same way, we can say that if you apply 5 Newtons, you apply 5 Newton force, so meaning you multiply this by 5, you also multiply this by 5. You will stretch the spring by 10 centimeters. If asked what is the Hooke's law constant or the spring constant, this is how you do it. The one that is shown to you here below. How you find the constant. Now, how do we use calculus in determining spring work? So, let's say a force of 20 pounds stretches a spring from a natural length. Take note, natural meaning this is the original length, 7 inches. Okay, the final length is 12 inches. So if this is the original and this is the final, then the disturbed length is 5 inches. So it's the X that you are interested in, not the natural length, but the X, the change in the length of the spring. So you just subtract from the stretched length the original undisturbed length of the spring. How much work was performed in stretching the spring to this length? So how much work was done? So this is the change. So in many ways, we are not at all concerned with the actual length of the spring, only with the amount of its change in length. Hence, we do not care that 20 pounds of force stretches the spring to a length of 12 inches, but rather that the force of 20 pounds stretches the spring by 5 inches. So we go back to what I have written here. So this is the change in the length of the spring, and you have the force applied, which is 20 pounds. So from in here, class, from in here, you'll be able to find the K, just like in the illustration that was used in the previous slide. So determining the K, so you have X or F is equal to K times the X. So you substitute 20 for the force, do not anymore place the unit, then you have K, and you have 5 for the inches. And since what goes with the pounds, class, is always feet, so you can divide this by 12 so that we can make the unit in feet. So I'll change this to 5 divided by 12. That way, the 5 inches here is converted to feet. So you will have a K value now equal to, check, what's your K value? times 12 divided by 5. Your K value is 48. 48 pound force per foot. So this is your shall we say, your Hooke's law constant. Okay, this is illustrated by the figure below. So this is the force and this is the corresponding elongation. Now, let's continue. So this is your Hooke's law constant, 48-pound force per foot. Right? Take note of that. So I will clear my markings here. Proceed to the next one. So converting the units of length to feet, we have done that already. So this is the K that was shown to you. So your force now, your force, again, let me annotate. Since you already have the K, your force is Kx, right? So you substitute the constant, 48x. And then you use this particular formula in determining spring work. So 48x is your force and this is your displacement. Your limit will be from 0 to 5 over 12. This is the change in the length of the spring. So from 0 change to 5 inches or 5 over 12 feet change in the length. So if you just substitute the values of the limits after you have done your integration here, which is 24x squared, you will have the answer 4.1667 foot-pound force. Okay, so very simple, a lot simpler than the previous problems on work because the key for any spring work is in determining first the K. How do we determine the K? Based on the condition that is given in the problem. So we're able to get the 48 from the condition that, so it was given already in the previous slide. Okay, let me clear my markings. So the 48 was taken from this one. 20 pounds divided by 5 over 12, converting the inches to feet. Okay, so that's spring work. Next meeting, we'll be discussing work in pumping a fluid out of the top of a tank. Now, this is a very common challenging problem in calculus, and I can remember during the time, my time when we had our board exam, this is one problem that I have to solve. Then, we have to solve our problem showing the entire solution. We don't have multiple choice then in our time. So, everything is being corrected, showing the solution to all the problems. Okay, so we will have this continued Monday next week.